In the previous lessons, I urged you to think a bit about your motivation behind attending this course. But now I want to take a minute to talk about why I think courses regarding statistical analysis are wondrous. Statistics is everywhere around you, from weather forecasting, financial markets, research in the medical field, to insurance companies. Statistics can be used in all fields to fine-tune business decisions or to help find cures to diseases. Now, I want this course to be a stepping stone for you to reach your goals. And with that said, a warm welcome to you from Shaw Academy, and thank you for choosing to study with us. In case you're joining us for the first time today, in which case I would recommend you to rewind and watch lessons 1 to 4. Your course educator is Marlies. My name is Nina Smith. I am the one behind the voice you're hearing now, and I will be presenting this course. This is your professional diploma course in statistical analysis, Lesson 5, Distributions. In the previous lesson, we introduced some basic concepts surrounding populations and samples. Lesson 5 will further elaborate on these concepts by delving deeper into the subject of population and samples. Thereafter, we will introduce random variables and distributions. Remember in the previous lesson when we talked a bit about the bell-shaped curve? Well, now we will finally learn what on earth that meant. We will end the lesson on a high note with more fun practical demonstrations in SAS Studio. So let's not waste any more time and get started with the first topic of the day, populations and samples. Let's quickly recap what we've learned in the previous lesson. We learned that a population can be defined as a large set or collection of items that have something in common. An example of a population is the census respective government collected every decade or so to collect information about persons living in the country. As you can imagine, this can be very time, resource, and financially consuming. But what happens when we want to find out more information about people in the country quickly? This task would be difficult with an extremely large group. We could conduct a smaller study based on a small proportion of the population. The proportion of the population is a representative of the larger group and is known as a sample. We can use the sample to make inferences on the general population of the country. Returning to our census example, in order to speed up the data collection process, the government could divide the population into areas, also known as strata, groups that carry similar characteristics. From there, a generalized result could be achieved for the areas not counted based on the strata's results. So why do we sample populations? Collecting a smaller group of data is less time-consuming and also much cheaper. Well, sometimes it isn't practical to sample the entire population, so we have to take a sample from that population to deduce information about the larger population. If sampling is done correctly, the sample can be more accurate than an incorrectly gathered population and might also be able to reduce heterogeneity in the data. The process of collecting information from a sample is called sampling. We use sampling techniques because we want to choose a sample that is a good representation of the population. In other words, we want to ensure we will be able to accurately infer valid results from the sample about the population. A few sampling techniques that we will discuss further in today's lesson include random sampling, systematic sampling, stratified sampling, and cluster sampling. These techniques assist the researcher to choose a sample that accurately represents its population. Random sampling, also known as a probability sample, is when a simple sample size of n is chosen in a way that every item in the population has an equal chance of being selected to be in the sample. A good example would be drawing names randomly from a hat. This is the most common way of sampling. Now, with random sampling, we're able to use statistical methods to analyze the sample results. Systematic sampling is when the population is ordered and items are chosen at regular intervals, such as every fifth item in the population. The starting point, however, is randomly generated. An example of this could be choosing every 10th name in the class, starting from the 23rd name in the list, if we want to eliminate the risk of skewing the data. Stratified sampling is when the population is divided into subgroups, also referred to as strata, based on certain common characteristics like gender, age, or income bracket. For example, if the class has 1,500 female students attending but only 300 male students, and we want to ensure the sample is an accurate reflection of the population, we could choose a random sample of each group by selecting 150 female students and 30 male students to be part of our sample. Cluster sample is when the population is divided into clusters or subgroups. Now, the groups all have similar characteristics. The subgroups are then randomly selected, and all the items that is chosen in the cluster are selected for the sample. This is a good technique for large populations that are extremely diverse. An example of clusters could be geographical areas such as districts, like metropolitan areas. Remember, all the summary notes and slides are available in your toolkit and would really be worthwhile to keep as a resource at your fingertips beyond this course. These will also help you prepare for your assignment that occurs at the end of every second lesson. Okay, moving on to random variables and distributions. In the previous lesson, we learned that a random experiment can be the throw of the dice, and the event the sum of the upward-facing dice. So a random variable is a variable with possible numerical outcomes of a random experiment, like the dice throwing example. A random variable is not the same as the algebra variable, for instance, x, but rather a whole set of values. The random variable can take on any of the values in the set and is defined in terms of the outcome of a process. A random variable can either be discrete or continuous. If we talk about a discrete random variable, then the random variable only takes on a countable number of distinct values, for example, 0, 1, 2, and 3. If we talk about a continuous random variable, then the variable takes on an infinite range of possible values. Now that we know more about random variables and how we use them, let's uncover how random variables tie in to distributions. Let's draw a random sample to obtain grades of learners for the quiz. As we obtain the grades, we can create a distribution of the grades. This is useful to us when we need to know which outcomes are the most likely to occur and what the spread of the potential values are. In other words, in either table, formula, or graphical format, we can see what the likelihood of the event or outcome is. A probability distribution is a table, function, or graph that describes the values of a random variable and the probabilities associated with these values. A probability distribution describes all the possible values and likelihood of the random variable in a range. Many different distributions exist, but today we will explore the binomial and normal distributions. Now that we know what a distribution is, we understand that distributions can be helpful to visualize what the outcome of an experiment might be. It's also important to note that the sum of all the possibilities of the distribution will always be equal to 1. So, when represented on a graph, the area under the curve of the probability distribution represents the sum of the total probabilities. Recalling that the sum of the total probability is always equal to 1, therefore, the area under the probability curve will be equal to 1. Probability distributions, just like random variables, can be divided into two categories: discrete and continuous. Think of it this way. If we once again look at the sum of the upwards facing dice and the probabilities of each possible outcome, we note that the sum total of these probabilities will be equal to 1. But the question we want to answer in order to understand the data's behavior better is what the probability distribution of the experiment is. By representing the probabilities of the sum of two dices in the form of a histogram, we're able to better understand which events are more and less likely to occur. This graph indicates the likelihood of the events for our dice example. The graph is just a way to visually represent the probabilities. We can easily see that the likelihood of the events occurring are not equal. The y-axis represents the probability of the event occurring, and the x-axis represents the outcomes. This probability distribution is discrete because there are only a finite number of outcomes the sum of the two dice can have. Once again, the sum of these probabilities is 36 over 36, which is equal to 1. The first distribution we will introduce today is called the Bernoulli distribution. Now, this distribution has two possible outcomes, success or failure. It's easiest to think about this distribution in terms of flipping a coin. The coin can either land on heads or tails. Therefore, there are two possible outcomes for a coin flip experiment. The Bernoulli distribution can be seen as the building blocks of the binomial distribution that we will cover in more detail in the next lesson. The next distribution we will introduce is the most commonly used distribution, which is the normal distribution. Now, this distribution represents the behavior that most often occurs in the universe. It's also known as the Gaussian distribution or the bell-shaped curve. The normal distribution is symmetric around the mean, and it is depicted as a bell-shaped curve when plotted. This means that half of the values are to the left of the center and the other half to the right of the center of the distribution. The mean, median, and mode are equal to each other for this distribution, hence the symmetry. The normal distribution is continuous, meaning that it takes on values from negative infinity to positive infinity. Once again, note that the total area under the curve, the sum of all likely outcomes, is equal to 1. The normal distribution is fully described through the mean and standard deviation. When we say that the normal distribution is described through the mean and standard deviation, we say that we can simplify the normal distribution using only these two parameters, the mean and standard deviation. The mean of this distribution is 0. The standard deviation is 1. The skewness is 0 and the kurtosis 3. But more on this a bit later in this lesson. Now, when dealing with a normal distribution, the standard deviation becomes especially useful. The empirical formula or rule says that when a random variable is normally distributed, 68.27% of data lies within one standard deviation of the mean. 95.45% of data lies within two standard deviations of the mean. And 99.73% of data lies within 3 standard deviations of the mean. From this rule, we can see that almost all the data falls within 3 standard deviations of the mean. This rule also helps us to identify outliers or extreme values in this distribution. There are certain assumptions about the sample we can draw if we know that the distribution is normal. But how do we know when this is allowed? Well, guidelines we can use to determine if the distribution is normal is to look at the sample size. If our sample is large enough, then we can assume that the distribution is normal. But what is a large enough sample size? Typically, a large enough sample size is a size greater than 30. Now you might wonder, where does this number even come from? The Central Limit Theorem states that if the sample is large enough, meaning if the sample is bigger than 30, the distribution will be approximately normally distributed. Now let's say that we decide to throw a pair of dice and sum the upwards facing dice, and we repeat that event 100 times. Let's say we repeat this experiment 50 times. Eventually, the more we do the experiment of throwing the dice, the more normal our probability distribution becomes, meaning the more symmetrical the shape of the distribution becomes. So we can see that as the number of trials we conduct grows, the distribution tends to normality. The Central Limit Theorem is one of the magical mathematical applications and will form the foundation to hypothesis testing techniques that we will discuss later on in this module. Let's evaluate a few of the distributions that form part of the red wine data set's variables. In the previous demonstration, this is more or less where we left off. Just to remind you, we investigated histograms of each variable of the red wine quality data set. We also investigated box plots for some of the variables. And then we also ended the lesson with some talk about skewness. Now, for this demonstration, I would like us to have a look at a few of the variables and see if we can spot if the distribution is normal or not. Our first variable is our outcome variable, quality. This is the variable that has an ordinal score ranging from 0 to 10. The values are discrete, meaning that it can only take on certain definite numbers like 1, 2, 3, or 4, etc. We found that the quality variable has the most amount of observations in the score categories of 5 and 6. Now, this variable contains ordinal values, and we can say that because we find most of the data contained in categories 5 and 6, the data is unbalanced. What this means is that this variable's data is unequally distributed. An interesting fact is that this type of data is very common when working with disease data, because generally this type of data would have a group of patients that is healthy and a group that has the disease. And if it's a very rare disease, the one group will generally have much fewer patients than the group that does not have the disease. So the way that we can deal with unbalanced data is to weigh these classes, meaning to attribute to a greater weight to the quality scores that contains less observations. But that is a more complex problem we will look at a later stage. For now, let's have a look at the density variable. As you can see, the median and the mean are almost exactly the same for this variable. The values are very close to each other. And if we look at the distribution curve of this variable, it seems as if the curve has a nice symmetrical shape around the mean. So maybe what we can do is create a histogram, and we can overlay a normal density curve for the density variable. So, just to get a better idea of how this variable behaves and if the distribution follows that form of the normal distribution closely, note that SAS uses the procedure sgplot to create a plot. And we are creating a histogram of the variable density, and we would like the scale to be count, not percentages. And then in the Appearance tab, we can tell SAS Studio that we want the density plot to have a normal density curve overlay. So we tick normal density curve to overlay that, and we can select to overlay the curve on the inside of the histogram. And we can play around with the bins at a later stage if it's unclear to see the distribution. Let's just first see how this graph turns out. Now we click on the running man. Okay, here is the result of the plot we created. The distribution of the variable seems to follow the normal distribution. It's especially relevant that this distribution tends to follow a more normal distribution in comparison to, for instance, the distribution of the total sulfur dioxide. The distribution of total sulfur dioxide is very skewed. If we create a histogram of the variable total sulfur dioxide and we overlay the normal density curve and run these steps, we note that there is no data contained in the lower tail of the distribution. It appears as if this variable's data might be truncated at the lower end. Truncation of the distribution could happen when the instrument used to measure the variable's values aren't able to measure certain values. We also note that the distribution has a very long upper tail. When a variable has a long upper tail, we say that the variable is positively skewed or right skewed because the tail lies to the right of the distribution. but we will cover a little bit more on this topic of skewness in the next lesson. Okay, so let's have a look at some of the other variables as well. Let's go back to all of our plots we created earlier and let's investigate the pH variable. As you can see, the pH variable has a mean and median that is also quite close to each other. If we create a histogram of this variable and we overlay the normal density plot to understand the distribution better, as we did with the density variable, we note that the pH variable also tends to the normal distribution. Okay, so what I would like to go do now, and I will list this for you in the challenge at the end of this lesson, is to go and have a look at the rest of the variables' distributions. See if you can spot if the distribution is normal or not. Think about if the data is skewed or not. Like I mentioned, we will be discussing skewness in the next lesson. But I do think it's important for you as an analyst to be able to research topics that you haven't explored yet and to problem solve unknown topics. Hence, posing this to you as a challenge. Good luck, everyone! For the last topic of the day, we will once again put the theoretical knowledge we've gained to the test with a practical demonstration. Practicing the skills acquired on a data set is equally as important as learning the theoretical knowledge. Now, I want us to once again have a look at the wine quality data set. For the last demo of today, we're going to learn how to do some basic data cleaning and data managing techniques. We're going to investigate and explore the data now. Now, as a first step, we will check if there are any missing values. After that, we're going to do some recoding of the quality variable. If you recall from the previous lessons, we discussed the quality outcome variable and we found that there are very little observations in the lower category scores. We said that we would group those scores together. So we're going to do that now, and then we will end off this demonstration by transforming some of the variables that we found to be very skewed in the previous demonstration. So let's check if there are any missing observations for the data as our first step. Once again, navigate to the task and utilities in your left-hand side pane and scroll down to Describe Missing Data. Double-click on that, and we are working with Import Data Set. Remember, this is a temporary data set. Then select all the variables, and now we note in the coding pane, the procedure that SAS uses is called the proc frequency procedure. Now, this procedure, we will create a frequency table, and with the conditions we have specified, list if there are any missing observations in a table format. So you can see proc frequency procedure produces one-way to n-way frequency and contingency tables. In other words, this procedure produces tables that will show if there are any missing observations in each variable. Let's click on Run. And the results now showcase the frequency tables. We notice that throughout all the variables, there are no missing observations. Each variable contains almost 1,600 observations. And seeing as there are no missing observations in the data set, we will not investigate missing observations further. Okay, so as the next step, I would just like us to have a look at the Data Exploration tab. I want to show you what the effect of outliers are on correlation. Okay, as you remember, many of the variables contains outliers. Outliers can skew the view of correlation between the variables, especially if they are prevalent in the variable. So let's just look at a variable that we know was fairly normally distributed, our density variable. And then a variable that we know was fairly skewed, the volatile acidity. The classification variable is the quality variable. And then run that. Okay, so you can see in the coding pane that we are creating scatter plot metrics. Do we need anything else? Maybe some plots? Maybe we can add some histograms with a normal density curve superimposed. and pair with the scatter plots. Okay, our results show a volatile acidity histogram and a density histogram with pairwise scatter plots and normality curves superimposed. I've also added a prediction ellipse at a probability level of 95%. Now, the pairwise scatter plots indicate to us the linear association between the two variables. They serve as a visual test for bivariate normality and indicate the strength of correlation between variables. The confidence ellipse shows where 95% of the data should lie, assuming that the data is bivariately normally distributed. And if we assume bivariate normality, the percentage of observations that fall within this ellipse should closely agree with our specified 95% confidence level. So if we adjust the confidence level, then we can examine the effect that it will have on our bivariate normal distributions correlations. This serves as an additional visual indicator of correlation besides the Pearson and Spearman correlation coefficients. Okay, scrolling down a little bit, we also included box plots in the results. We've created a box plot for each score of quality. It appears that there are some outliers in the scores, specifically the upper scores for the volatile acidity quality scores. The density by quality variable also contains some outliers. We can conclude that there are definitely some outliers in the middle range scores of the quality variable that we need to investigate. A possible approach to this problem is to remove the outliers and model the data without those outliers, and then model the data with the outliers. Then you would compare the two results and conduct what's called a sensitivity analysis to see what effect those outliers had on your results. But for now, we're not going to go through that rigmarole because it's quite an extensive procedure. So next up, I would like to show you how you can recode the quality variable's values. Choose the option Recoded Ranges in the left-hand side pane because we want to recode the range of the quality scores that fall. Let's select our quality variable and we can call the new variable Recoded Quality. And just note that if you enter a space, the naming convention is not valid in SAS. So we have to use an underscore, or I think you can also use a point. But for now, let's just use an underscore. The values that we want to recode is if the numeric value of the quality variable falls between 0 to 3. We want to recode these values to the category poor quality wine. And then if the values fall between 4 to 6, we recode these to the category average quality wine. Okay, and if the values fall between 7 to 10, we will recode these to good quality wine. Here you can see once again the coding pane that we are now using, the work import dataset, the temporary dataset, and we recoded the quality scores between 0 to 3 to poor, 5 to 6 to average, and 7 to 10 to good. SAS will create a new dataset for these recoded variables. It is named the Recoded Ranges. We can create a new dataset, or we can write it to the original dataset, which means it will probably overwrite our original dataset. But I want to show you a comparison between two variables a bit later. Therefore, I'm not going to overwrite the original dataset, but rather create a new dataset. Let's click on a Running Man icon again. And now you can see that it's recoded all the values of the quality variable. If we navigate back to the Data Exploration tab and select the recoded ranges dataset as the input dataset, and select the continuous variable to be the fixed acidity and the classification variable qualities recoded new variable, meaning we use the new variable that we created, recoded underscore quality. Now from the results, we note that the quality scores are grouped into average, good, and poor categories. And that is a little bit on how to recode variables using SAS Studio. Now moving on to the final data management and cleaning exercise for today, transformations. The reason why we do transformations is because we want our distributions to tend to normal as much as possible. As you know, the normal distribution, also known as the Gaussian distribution, is one of the most common distributions used. When we know that a distribution is close to normality, meaning that the distribution is symmetrical around the mean, in other words, the right side of the probability distribution and the left side of the probability distribution looks more or less the same, there's a lot of assumptions that we can conclude about the variable's behavior. For instance, if we know that the distribution is normal, we know that within one standard deviation, approximately 67% of the data's observations will lie. This information allows us to easily estimate how volatile the variable is if we assign a certain amount of confidence to that variable. We can then easily tell how likely it is that the predicted values will fall within that range. Let's click on the Transformed Data tab and use the original data set again. We choose the variable volatile acidity that we found to be quite skewed. Note that there's a few different transformations that can be applied to this variable. Now, the reason that we apply transformations to variables, as mentioned, is to try and transform that distribution to appear more normal. Okay, so if we select the natural logarithmic transformation, in the coding pane, we observe that SAS has created a new variable called log volatile acidity. And it is literally multiplying the natural log with the volatile acidity variable. Okay, now let's run this. And then we can create plots. Okay, so select histogram. And we use the work import, the original data set, to first just create a histogram of this variable again. And let's create a histogram of the transformed variable. Now that we use the dataset work transform and select the log volatile acidity variable. This is now the transformed variable's histogram. And we note that the distribution is now much closer to a normal density curve than the original untransformed variable's distribution. Observe the original variable has a long tail, and the observations here to the left-hand side to the lower end looks like it was cut off a little bit. So transforming this variable helped lessen the skewness of the variable. But there might still be some outliers contained in the variable. Maybe we can just also have a look at the summary statistics and compare that of the transformed and original so that you can also get an indication of how the skewness value reacts when you transform a variable. Let's navigate to the summary statistics and just quickly create summary statistics for the fixed volatile acidity variable. We include the variance and the skewness. Okay, and then we will run that. Remember, this is the original data set's results. Now we create summary statistics for the transformed variable log volatile acidity. This is the transformed variable, and we choose the quality variable to classify by. Whoops, I forgot to include the skewness statistic. Variance, skewness, and we click. Okay, when we look at the original variable, some of the values here tended to be close to and higher than 1. For instance, the quality score of 8 had a skewness value higher than 1. These variables were quite close to 1, and this one was also close to 1. When we log the transformed volatile acidity variable, the transformation brought skewness values down, so to speak. The quality score that had a skewness value over 1 is now lower than 1, and the scores values that were close to 1 is also lower. Therefore, the transformation generally lowered the more extreme skewness values, which is good because ideally we don't want the data to be severely skewed. We want the data to tend close to normality. Okay, guys, and that is a little bit on how you can transform the data set and things you can look at for now when you're dealing with data that might not be normally distributed. The world is changing faster than we've ever realized, and statistically, the job you will do in the future is most likely not the same job you originally qualified for. To future-proof your career, you need to strive to constantly update and diversify your skill set. We are in a digital age and are at the point in history where higher education is no longer only available for an elite few. At Shaw Academy, we believe that students can build your own credentials, design your own learning, and develop a multitude of skills. So why not think about what you want to do beyond this module or beyond this course even? At Shaw Academy, we offer different memberships that will fit your lifestyle and learning pathways to enable you to build your own skill set. As we've done in today's lesson with a few of the variables, I would now like you to try to identify the distributions of each of the red wine dataset's variables. It's okay if you have to research the distributions while you investigate the histograms. That is all part of the constant learning process of an analyst. And just like that, you've completed another lesson from the Probability and Statistical Analysis course. I look forward to seeing you for the next lesson.